This is Farhan from AlgosFromScratch, and I welcome you to this amazing YouTube playlist on building DistilBERT model from scratch using PyTorch. In this video, we are going to start the most important part of this playlist and also the model, that is the multi-head attention. If I show you this in the original paper here, you can see we in previous lecture we built this scaled dot product attention that was basically a single head. Now we are going to build this multi-head attention where we will have multiple heads for these scaled dot product attentions, and in each head we are going to perform the same steps, okay, and then we are going to concatenate them by the end and then pass it through a linear layer, okay. So this is the same concept, but in this multi-head, we are just executing the parallel heads rather than just one head, okay? The topics that we are going to cover, first of all, let me just tell you why we need to have these multiple heads instead of just one head, why these multiple heads are going to perform better, okay? So let's say you are working on a project, and that project is about like research, designs, and then writing the documents, etc. So here's the thing. First of all, let's consider you are alone working on that project. So what you will be doing, you will be working on all of its angles like research, design, documentation, etc. And you will be just not focusing on each part, okay. So that is the single head, okay. Now imagine if you have three experts, and one is expert in designing, one is expert in research, and one is expert in the documentation part. So they three work in parallel, okay, and they by the end they sit together and they share their opinions, okay. You can fit this analogy on this single head and multiple head attention mechanism, okay. The mechanism basically same, but this is just a bit of smart work, okay. If I just give you a short definition, so a single head is forced to compress every possible relationship into one averaged view, whereas multiple heads let the model run several specialized attention patterns, like the same attention mechanism, but they will be specialized in their specific heads, okay, and then by the end fuse their complementary insights, okay. So with this, I hope you understand why we use this multiple head attention. And if I just show you this right here, the research paper also gives the same kind of definition, and they say instead of performing a single attention function with this is, so we keeps values and queries, we found it beneficial to linearly project the queries, keys, and values h times with different learned linear projections. Multi-head attention allows the model to jointly attend to information from different representation subspaces. So these subspaces we are going to create, okay. We will be creating some slices of this long 768 dimension, and we will be passing each slice to its specific head, okay. This was a simple understanding of why we need this multiple head attention and why the single head attention won't work, okay. So let's understand where the split basically happens, okay. First of all, you can see here we have this input embeddings, okay. So from this point we will get the input embeddings, okay. I have this 1 5 12 shape example, okay, because we will be performing hand calculations, so I cannot perform hand calculations on the original size, okay, and the original shape. So this example we will be using, okay. So here one is sentence, and each sentence has 5 maximum length, like instead of 128, and for 768 we have 12, okay. So this comes from the input embeddings, okay. And here we will create the query, key, and value projections, okay. And these are also going to have the same shapes, okay, like this. Now if I just show you one head in detail, and these two remaining heads will have the same sequence of operations, okay. So here you can see when we split it into 3 heads, we convert it to this shape. So previously we had 1, 5, 12. We convert it into 1, 3, 3, 4 heads, okay, and 5 the sequence length, and 4 is the dimension of each head, okay. So we split this 12 into 4. It means we are splitting it into 3 heads, okay. So 12 divided by 3 equal to 4. Now this is going to be executed in parallel, okay, because this pair will be treated as a separate batch. These 3 heads will be executed in parallel, okay. One head here you can see is this one, okay, and in each head we perform the same operations that we performed in the single head attention, okay. So head one, first of all we calculate the scores, that is q, k, t. Then we perform the scaling, okay. So same steps, and here we will divide it with the dimension of k, okay. So in this case dimension of k is going to be 4, and it will be the root of 4, k square root of 4, and it will then be 2. So this is what we are going to divide this qkt with, okay, the original formula of attention, okay, and that is qkt divided by dk, okay. And then this we are going to pass it to softmax function, okay, and the result we are going to multiply with the values vectors, okay. And in between the like this first step and the softmax, we apply this mask, okay. I've explained why we apply this mask, okay, in our previous video where we applied it on the single head. Then we apply this softmax, okay. So softmax will be generating the probability distributions for each token dimension. The result we are going to multiply with v, okay. And same goes for these 2 heads, okay. And these 3 heads are then going to be concatenated, okay, and we are going to get the same result, 1, 5, 12. So all of the 3 heads, they will be placed side by side, and we will get the same shape as an output from these 3 heads concatenation, okay. And then we will pass it through the output projection, okay, and we will be getting the output of this multi-head attention block, okay. So with this, now I will just move on to the coding screen. So this is the same notebook we have been working on, okay. So if I just print the model, this model is the original model, okay. And this distil DistilBERT self attention. In this, you can see we have Q linear, K linear, V linear, out linear. So it would be an just a linear, no, with no activation function, and then this dropout. Okay, so we will build this part. Okay, and let me just copy it. Okay, and I will just paste it over here. Let me clear the output. Okay, and over here I am going to start with, okay, so first of all let me just execute this part of code. So okay, this is the model config that we are maintaining for all of the classes. Okay, so this was the embedding class. Let me check if it's working. Yeah, it is working. Okay, this was the naive classifier and we tested it. It gives us the logits working fine. This single head we created in our last video. Okay, and you can see this gives us the output of this shape. Okay, now in this we are first of all going to build our class, and this class I'll call it multi-head attention. Okay, this multi-head attention I am going to inherit it from nn.module. First thing that you need to do is to define your constructor. Okay, in this constructor now I first of all will pass the self. Okay, then the second parameter that I can pass here is, okay, the number of heads. Okay, because you know this is the very obvious parameter, because this is what we are going to do in this multi head attention class. Okay, number of heads 12. Okay, what else? Okay, so if you look into this here you will find we have dimension. Okay, so first of all here I will add number of heads, and number of heads is going to be equal to model config, and I will extract the number of heads from this dictionary here like this. Then the next thing is I am going to get this dimension. Okay, so dimension is going to be equal to model config dimension. Yes, good. And then the next is the dropout. Okay, so I am going to have the specific dropout key value pair in my model config dictionary. So I will just call it, first of all I had this dropout embedding. Okay, here I will just make the drop out multi-head attention. Okay, and this is going to be equal to 0.1. Okay, and let's execute it. Now with this, the next thing that is I guess that is pretty much it. If we need anything we will be adding them. Okay, and let's just start with the first Q linear, K linear and V linear. Okay, so I'll just start with self dot. Okay, so first I will take this number of heads. Okay, and self dot number of heads is equal to number of heads. Okay, second thing I want to do is, okay, that is the, okay, let me also verify that my dimension size is properly divisible by this number of heads. So this is the must condition. Okay, if this uh, is not the case, we cannot then have proper slices for each head. Okay, so it will be something like dimension, and it must give us the number of heads, so it must give us 0 remainder. Okay, this is the must case. Okay, and then I can calculate the head dimension. Okay, head dimension, as I mentioned earlier, so it is going to be the like dimension size divided by number of heads. Okay, so it will give us the head dimension, like how many uh, numbers from the dimension uh, we will get in one head. So if we have like 768 and we divide it with 12, so we will get 64 dimensions for each head. Okay, so each slice will have 64 values. So this is what we are going to have in the mm, okay self dot head dimension. Now the next thing that we are going to initiate is q linear. Okay, q linear, k linear, and v linear. Okay, and let me just check these suggestions if they are okay. Yeah, they are okay. Okay, so the next thing is we are just going to okay, these are the two suggestions. So if I quickly check them out, linear in feature 768. Okay, so dimension 768 and out feature also 768. Dropout will be coming from the MHA. Okay, so yeah, I'm just accepting these suggestions. Okay, and I think I need to add it right here. Okay, so the drop out is dropout p is equal to this config value. I'm just going to cut it from here and paste it over here. Okay, then I will just add the dropout p here. Okay, and the final yeah, I think that is ready. Okay, just let me quickly check. Okay, 768 768. Okay, yep, everything is done. Now the next part is we are going to start building our forward method. Okay, this forward method is the very first part of this. It will uh, take the input embeddings. Why? Because we are going to build we are going to initiate the QKV projections from the input embeddings. Okay, so self, okay, and then input embedding. So if you remember from the single head, we are going to have the same uh, values, okay, as an parameter over here to the forward method, that is input embeddings and attention mask, because internally we are going to perform the same operations. Okay, so these are the two parameters we are going to pass to the forward method. And inside this forward method, first of all, I will just quickly create the query that is going to be this self q linear. I will pass the input embeddings and I will get the same shape for cube. Okay, similarly for k, and these suggestions seems correct. Okay, let me just check them. Yep, they are fine, so I'm accepting them. Okay, now here is the next part where we are going to perform the split. Okay, so I will split these values, these QKV projections with the help of this generate split or generate heads. Okay, so here in this, each time I will get just one projection like Q, K, and V. Okay, so let's just call it X. Okay, batch size here too. Okay, now I will also create the batch size here. This batch size is basically the input embeddings dot shape, and from the shape I will just get the zeroth value. Okay, and it will give me the batch size. I can pass this batch size along with query key and values to this generate heads, and it will split the query keys and values into the multiple heads. Okay, like this. So when I will pass these queries, keys, and values, this is the uh, you can say split that we will get. Okay, so for head, for first head we will get this QKV. So if you as I mentioned, this is the example with 3 heads. Okay, and we will be calculating these 3 heads example. Okay, with hand calculated values, and here we will be just having the uh, 12 heads. Okay, and 768. Okay, so here now this batch size and X now going to give us the, okay, so on each X I will call the view. Okay, this view is going to be, okay, so first let me just explain it right here. So let's say I have 128 768 dimension of query. Okay, and I pass it to this splitting head. Okay, what I want to have the shape that contains first 2 dimensions, like this one is batch where it is 1. The second dimension I want is the number of heads. Okay, so this is going to be 12. Okay, and then 128, that is the sequence size, and the dimension. Okay, dimension, if you just divide 768 by 12, you get 64. Okay, so this is going to be 64. So we will get this shape. Now how we can get this shape? First of all, what we do, we will split this dimension into 12 slices. Okay, and then we will at this stage we will have a shape like 128 12 768. Okay, then we will swap these two positions. Okay, so this batch size and the heads will pair for the parallel computation. Okay, so each head will have this sequence length plus the dimension. So that is what we are going to do. Okay, so the final output we are going to have is 1, 12, 128, 64. Okay, and for that I will call this view. Okay, so the batch size is going to be same. Okay, so I will just uh, accept this batch size over here. Okay, then the second thing is I just want to have the sequence size. Okay, so let me just create the sequence size here too. Okay, so self dot sequence size. Okay, no, I don't want it right here. Rather, I can extract it from this input shape and then Q. Okay, so let's say that X dot shape, and initially the shape of the X is one, that is batch size 128. Okay, so I can say that anything at position 1. Okay, and that value I basically want to have at this. Okay, and then the number of heads basically. Okay, so self dot number of heads that I want here. Okay, uh, like this 12. Okay, this value right here. Okay, and then okay, so once we have 12, so my bad, then this is not going to be 768, it will be 64. Okay, so then the head dimension. Okay, so I'll just call the self dot head dimension. Okay, and I think it is ready. Just one thing, now we have this 1, 128, 12, 12 and 64. Okay, but we want something like 1, 128, okay, sorry, 1, 12, 128 and 64. Okay, so each head will contain all the tokens, and the 64 dimension values. Okay, so I'll just swap these two. Okay, so if I just swap these two, these are at index 1 and 2. Okay, so I'll simply call the transpose. Okay, and I'll pass 1 and 2 over here. Okay, and I think this is done. Now I will just return 8. Okay, and yeah, I'll just return the overall this complete. Okay, and let me just, yeah, that is pretty much 8, I guess. Let me verify it. Call this self dot generate. Okay, and generate heads. Okay, and in this generate heads I will pass Q. Okay, and that is what I am going to test first of all. Okay, for this I will copy all of this from here, and I'll just come here and paste it. Okay, now here I'm just having this one sentence, input IDs and attention mask. It gives me the input embeddings. Here I'll create the attention, let's call it multi head attention, multi attention object, and it is going to be equal to multi head attention. And then here I'll just say multi attention. Okay, and this multi attention will have the, okay, so I'm getting this return, so just say testing. Okay, testing. And this testing, if I just print the testing dot shape, okay, let's execute it and check if we have any. Okay, so we'll generate had missing one. Okay, batch size, we are not passing the batch size here. Okay, so I will also pass the batch size. Okay, and yes, that is it. So we have 1, 12, 128 and 64. Okay, so this is what we wanted from the generate head to do. Okay, now once this is done, I will just quickly call this generate head on all of our Q, K and V. Okay, so this is how we call them. Okay, generate heads, Q batch size, K batch size and V batch size. Okay, and yeah, when I call this, what I get as a result, I get, like, here we have 3 heads. So we, for our example, we will have head 12 heads. Okay, and each head will have its own part. Okay, so that is how I will have all these heads and their slice values. So each head will have all the tokens. Okay, so let's say here is 5 tokens, so we will have 128 tokens in each head. Okay, and each head will have these values like 64. Okay, here we have the shape is 1 and the head size is 3. Then we have 5 sequence length and 4. Okay, but in our case we have 1, 12, 128, 64. Okay, so it means we have 128 tokens in our each head, and for each query key and value we have 64 values. Okay, so this is the query of head 1, this is the key of head 1, this is the value of head 1. Okay, now if you just remember from the previous step, we execute all these heads, like these 12 heads in parallel, and each head will perform these tasks in parallel. Okay, and finally when we have the outputs of all the heads, we are going to concatenate them. Okay.